Okay, I'm sorry. My name is Corbin Cobalt. Welcome to Physics 221. Hesitating because I hoped and expected we would have a video recording going on today, and I don't see media vision people here. So it's a little disconcerting. I'm going to wait just a minute, see if I can come up with something that helps the process a little bit. Okay. Well, Michael, go ahead. I can't magically leave that video. I'll check with them and see. But there are a number of you who are here. The class is size is about 85 students, and there's about 15 who can't be here for quarantine reasons. Hoping to have the lecture videotape. But I'll do the best I can. I've got my video, my laptop running, but the microphone is not the best. So if you're picking this up after the fact from the video, I apologize for the technical problems, but I'll see what we can do to improve it for the future. So this course is Physics 221. It's modern physics. My name is Corbin Cobalt. I'm the co-chair in the physics department. I've taught this course before, but the last time was about 15 years ago. I'm the secondary instructor for the course. The reason I'm the secondary instructor for the course is that the physics department has been in a process for hiring a new instructor, a new faculty person to take on this course. That hiring process got delayed through no fault of anything other than the usual contingencies and chaos of the effects of the pandemic and trying to coordinate things in the current environment within the university. Our hope and expectation is that the new instructor will be named and put in place on time scales of days, not weeks. But in the meantime, I don't know if you're familiar with the term VAMP, but I'm going to be basically running the course at least the lecture part of the course until such time that the regular instructor comes in. In the meantime, we have a second. There's another instructor for the recitation component of the course. So just to be clear, this is as far as I'm aware, it's the only physics course that has an associated recitation. So the lecture meets Monday, Wednesday, Fridays at this particular time. But every Thursday, there's a recitation section. And I strongly urge you to go. The recitations are basically, we take this relatively large class, we break it into two, and each of the two groups gets hands-on, gets a chance to work in teams on problems and to work with an instructor. That instructor is Kurt Hinterbickler. He's excellent. He's one of the best teachers in the department, and his job will be basically to sort of fill in for some of the details, especially in the context of working problems for the homework and preparing for exams and so forth. He will be able to really give you some, I would call, a deep insight. So plan to be at your recitation sections to get the additional information that you want and have a chance to really work on the problems in the class. So what is this class? This is a sophomore class in modern physics. Who's it for? It's for physics majors. It's for students in any STEM field of science or engineering where an understanding of what modern physics is beyond the first year is important. I mean, everybody in this class has already finished and conquered, in some sense of the word, what we call the classical physics world. So we're going to spend a little bit of time at the beginning, sort of jumping into the modern world. And when we say modern, there's a little bit of a misnomer because modern physics has its roots as long ago as the late 1800s or the early 1900s. Basically, the 20th century corresponds to modern physics. Just to make, tell you what the topic is. So if I say we're going to talk about what's called classical physics, then classical physics falls into two large camps. The first is what we call, at least these days, what we call Newtonian mechanics. So this is the study of the motion of particles and bodies under the influences of forces, and Newton's laws, and of course the mechanics, F equals ma, and all of the language that's associated with that, kinematics. That's all part of classical physics, classical mechanics. It's also true that it's relatively straightforward, although sometimes mathematically tedious, to re-articulate Newton's mechanics in the context of the force laws as laws of motion into alternate description of the physical world in the context of what you might call general overarching category of conservation laws. Those notions of energy, momentum, angular momentum, all of these can be equivalent reformulations of Newtonian mechanics that were developed over the centuries to deal with ever more increasingly sophisticated problems in motion. And what's amazing, really, from the point of view of the history of science and technology in the world, is how successful Newtonian mechanics was for hundreds of years in basically describing and ascribing the phenomenon that were observed in the world with careful observation. Everything from you know, the nature of objects that you see in a macroscopic world, to understanding the tides, to you know, the workings of machinery, and so forth. Another branch of classical mechanics that really derived itself in rather later, of course, is the second course. Okay, this corresponds to physics 121, if you will. Is Maxwell's electromagnetism. So this all derives from all the experiments and works that were done into the phenomenon of electricity and currents, of charges, and came to this, essentially this brilliant integration, this unified picture of how the electromagnetic phenomenon can be explained by a set of four interconnected equations, Maxwell's equations, which you can write in two different forms, differential and integral, which explain not only the phenomenon that were being observed in laboratories with everything from radio frequency detectors to magnets and needles, but also fundamentally explain this much larger human experience of electromagnetic waves, of light, frequencies all the way from the radios to down, a whole rich world of what's called classical electromagnetism that was basically put forth in the mid 1800s. And we have to throw into this somehow, basically what we call, I'm going to put this in a very broad heading, statistical physics. It's very broad in the sense that the phenomena were investigated in the 1800s, and which were only because it's always sort of interesting topics that were studied, and I would call, in some sense, the word algebraic, because the systematic description of physics of what's happening at the microscopic level for explaining everything from the flow of heat to the pressure of air to the change of phases within materials, and trying to understand what the nature of fundamental constituents in that work, how the atoms go together, how these things were tangled up here. But there's basically a classical vision of how these things work that could be basically brought to bear on these different things. And just some of the and a few things like that. And these are topics that, generally speaking, aren't covered in your first year of classical mechanics. So we're going to spend a little bit of time in this class touching on statistical physics. You know, we'll basically take a quick look at thermodynamics and we get into the I would call more esoteric and pure modern topics. And it's not quite fair to say that there was a break in some sense. As we'll see, the evolution from the classical vision to the modern vision didn't happen overnight. It's not quite. But having said that, it's interesting to ask the question now, more than 100 years later. Once we get to the end of this, where would the world be if this is as far as we've come? If you lived in the US or Europe in the mid to late 1800s, and you were, in some sense of the word, an aficionado of the development of physical science, you would have the general impression, based on the way the materials were being presented, that that as far as physics was concerned, the game was more or less coming to an end. Yes? I mean, what is physics? Physics is the fundamental. What is physics? The answer, in some basic way, is it is the enterprise and the activity and the philosophy of study that tries to ask the question at the most fundamental level: what is the cause of the phenomenon in terms of the physical world? And that has to do with basic. So there's this, in some sense, the word fundamental or elementary aspect to it, in terms of how are things made up, what are all the interactions between bodies, what are all the what is the deepest level in terms of cause and effect? What can you say about the things that you actually see in the physical world? And if once you had classical mechanics, electromagnetism, and at least enough thermodynamics and kinetic theory to kind of explain things like the gas law and so forth and so on, you could look at the world and say pretty much everything we see can be explained. How would we explain in detail? And sometimes there were some puzzles that didn't quite make sense. But in terms of the attitude of the time, there was this sense that in terms of the human enterprise of physics, we had more or less conquered the nature of reality, and there was detail at the smallest scale, say within the atom, or really what's going on in the universe as a whole. But maybe there's a few strange phenomena that we don't really understand. We'd like to try to put it together at least, and then a few problems, especially in statistical physics, where things seem to not fall into place quite as tightly as can certainly set up these confusing things. And if we lived in that world, and that world had continued, what would we have? Well, we'd have, the Industrial Revolution as it happened. We'd have the concept of machinery. We would be able to use electrical devices, everything from lighting to machines. You could imagine, at least conceptually, you could imagine building, certain kinds of technologies to a highly refined level without any further modern physics. So, for example, you might talk about the space station flying humans to the moon, what was required to do that, and a case can be made that you could get to the moon with a physics understanding and the subsequent engineering understanding of physics based only on the classical ideas. So such a world could have existed, okay? But there's other things that wouldn't have existed. Now, when we talk about modern physics, we're basically talking about two things. The first thing we talk about in the context of modern physics is Einstein's relativity. So we're going to start with Einstein's relativity today, and just for the next actually 2 or 2.5 weeks. And then the other large field that basically corresponds to what we would call the fundamental introduction of modern physics is what we call quantum physics, quantum mechanics, and all of the things that follow. So what do these things give us in terms of the modern world, in terms of the impact that it has on our lives? Well, the easier one to point to is quantum physics, because without quantum physics, without an understanding at a fundamental level what was going on in terms of the way that particles at the microscopic level interact, that the nature of interactions between atoms and between particles within atoms have some and nuclei and so forth. But these interactions are governed by a completely different set of rules than what appear to govern the rules of classical electrochemical. Turns out to be fundamental for understanding, developing, and implementing all kinds of technologies that we take for granted in the 20th the notion of the way that transistors, semiconductor transistors, and all of the technology that's based on an integrated circuit is the design of those materials. All of that is fun. I mean, I wasn't just about quantum computing. Transistor is a quantum device in some fundamental way, and so we're already doing quantum computing in that sense. So I mean, you could build a computer out of a machinery, and in fact, the notion of a computer made from machinery is when initial concepts of Turing and others were put together. But you could not have anything like the power that you have in a cell phone. So everything that our modern technology depends on in terms of modern telecommunications, lasers, the whole business, none of that. Relativity, well, you'd say, well, relativity, that's for the cosmologists, for the space physicists, and everything. Here's how it depends on relativity. If you have satellites, the satellites out there, the satellites themselves have those comet clocks, and then those comet clocks are manifestly quantum mechanical devices. But even if you ignore that fact, and just said, look, we need relativity to understand what you are how you should achieve this. It turns out that the effects of the distortion of space and time, the motion of the satellites, plus the distorting effects of the Earth's gravitational field, which is again a relativistic effect, all of those things add up on the order of 3 to 700 meters position on the surface of the Earth. So that means that if you took Einstein and said, no, I'm sorry, I don't need to worry about relativity. Relativity only comes into place when things are going really fast, or when near a black hole or something really extreme like that. No, without relativity, instead of being here for class right now, you'd be basically on the other side of the way oval, wondering what to do, right? So our modern world depends critically on these things. So in some sense of the word, what is this class? This class is exploring the fundamentals of relativity and quantum physics. But this is important. So we're exploring it from the point of view of what can we say after having equipped ourselves with a year's worth of classical physics in these two major areas, Newtonian mechanics and Maxwell's equations. In other words, these topics are deep, and you can study them at an introductory level or a deeper level, but you can't go. You can only go. How I'm going to put each of these subjects can get deeper and deeper. So we're basically saying what would we with tools that we put ourselves here of basic physics and math. And then the second, so there's these two fundamental things which we'll take a look at. And then the second part of the course is basically once you now have added modern physics, the fundamentals of modern physics to the fundamentals of classic physics, what can you say about certain particular things in the universe? In other words, we're going to take a look at what we would call special topics, a subset of special topics in modern physics that whose advancement and understanding is only possible with these things. And again, we're looking at them with the eyesight of somebody who's been equipped with a little bit of understanding of these two things, plus the year that we've already had in our pocket for classical mechanics. So we're going to look at everything from the physics of solid state materials, the nature of semiconductors, scientific components, this kind of thing. We're going to have a look at the phenomenon of the quantum mechanical effects on some statistical phenomena, including multiple materials. We're going to look at the materials of some magnetic materials, some very rich properties. So we're not going to go into everything, but a little bit about the magnetic properties of materials. superconductors and so forth. And I then moved to what I would call the top areas of fundamental physics. So instead of just applications, what now that you have this thing, what can you say about the deeper nature of reality? Everything from elementary particle physics, elementary particle physics, quarks, leptons, standard model of physics, and then looking up to basically astrophysics, phenomenon that when we added just a little bit of Einstein's general relativity, what we say about the universe as a whole, cosmology, how the universe changes, how it's evolving now, and what we can say about it. So that's a big subject. And in fact, if you think about it, this course is basically everything that's important in physics after the first year. Yes. And one of the reasons that this course is offered is because for some reasonable chunk of you, this will be the last physics course you take. I know some of you are going, okay. And if this is the last one you're going to take, then this is our last chance to tell you all the wonderful things that you ought to know and that could be important to you in your life. But it's also a chance for those of you who are in physics or you're planning to study a field that is, in some sense, the word closely related to physics, in other words, that connects either technically or topically with some of these subjects. How can I put it? This course is your chance to see the exciting stuff. If you've been studying a year of physics, you've been studying material that's between 400 and 150 years old. Yes? And physics is fun, but you know, when I sit down and do physics research, I'm an astrophysicist. I study the origin of high energy phenomenon, cosmic rays, gamma rays, all coming from outer space, trying to understand, build devices to detect them, trying to understand where these things come from, what it means for the universe. If I'm doing that, I'm not, this is not enough. I've got to build up this. In fact, I've got to build a lot more of this, right? But at least at this point, you get a chance to get a taste to see where we're going. Right? It's important to do this. And to be perfectly honest, in a certain sense, this course is controversial. And it's controversial because in other words, to go from what we're going to do is we're going to taste of these things and then jump to the 21st century. And when I say taste, what I mean is we're going to spend a few weeks looking at the fundamentals as far as we can from this point of view. But our approach is not going to be pedagogically rigorous. I have not been standing in front of the top and derived computers versus can after me. I do watch the derivations of fundamental equations in relativity on physics. If you're a physics major, you will take a class in the future where such a thing is done. Yes? But I'm going to do this class. So I'm going to go, here's the idea and jump to the result. Yes? And if that bugs you, and by the way, not about substance, it was capacity. Why do we do that? That's not in some sense where physics is an axiomatic discipline. No, it's in principle, even if not in practice. It's built up of a logical sequence of steps. They basically make a mathematical argument that the following ought to be true based on these assumptions. And we tend to teach it that way. Yes, that's what it means to go to physics classes, to say, okay, here's how we're going to derive, whatever your favorite thing will be. And we're sort of somewhat deliberately not doing all the details. We're a little bit waving our hands, okay? But and that may bother you, but here's the promise. The promise is that even though we're doing this, we're not asking you why. We're saying, we're just showing you where you can go, and then we're going to let you and your future education, as you need it, to fill in those logical steps if you need it, right? In your life, right? And for that particular thing. You may find it perfectly good to understand in detail how a transistor works without understanding its fundamental properties. But someday you may need to understand those fundamental properties because that particular resistor that you're working on isn't behaving the way you expect. This course will not equip you to understand those fundamentals as in your brain, but it will equip you to understand that there are fundamentals and you can basically learn. How to put it? This is not a course that will tell you everything you need to know, but it is a course that will show you a map of where you can go
which you can use to teach yourself what you need to know as you get there. I mean, how can I put it? Isn't that the point of an education? We're not here to learn a bunch of facts. We're here to learn how to teach ourselves what we need to do those amazing things in the future that we haven't yet done. And by definition, those things aren't things that can be taught in class because they're new things, they're exciting things that people haven't come up with. If all you can do is solve the old problems, you're not ready to solve the new ones. So what we're doing is we're equipping you with a map of this basis, this amazing knowledge of modern physics to move forward. Right, so that's my motivation. I'll get off the lecture and stop delivering the sermon, the soapbox, or whatever you want to call it, and instead I'll start talking about the topic 10. Before I do that, just a couple of comments. Yes, the logistical organization of this class is getting there. Yes, we've got a basic syllabus in place. We're going to fill that syllabus out so you can see which topics are coming when. I'm working with the soon-to-be instructor to figure out who's going to do what, where, when. Once that's filled in, you have a schedule. We will have 2 midterms and a final. The first midterm will be at the end of September. The next one will be in mid to late October, and then a final. There's no lab. Yeah, no lab for this course. Doesn't be how we okay, know that. Again, the recitation. Is the recitation mandatory? We're not, I don't, there's no part of the grade there's no part of your grade that depends on whether you attend either this lecture or that recitation. But if you don't go to recitation, you'll be missing out on material that is, it's not that we have specific plans to introduce new material, but it's recitation that lets you contend with these really unfamiliar ideas in the context of a situation where you get to work your own problems and you get to work with the instructor. So, will everybody decide that, is every recitation going to be worth its weight in gold? Maybe, maybe not, but it's planned to be in this. All right. Textbook questions. So I got a bunch of them on email. We have picked a textbook. One of the benefits of the textbook is it's relatively inexpensive as an ebook, and so you can get it quick without having to wait for it at the bookstore if you wanted to read it on your laptop. Is that the only textbook that we're going to use? I'm going to put it. There are 4 or 5 different, probably more like 10 or 11 different textbooks, all of which have the title Modern Physics or some flavor variant thereof. They're all pretty much the same. They have slightly different. Some, for example, you'll see right away. I'm going to use some. There's a question of do you use U or do you use V for the velocities and special relativity? You can swap them, and you have textbooks that have them just swap. Is that okay? As far as I'm concerned, it's just fine. It's the same material. I give general assignments, but our plan is to basically provide a framework in the context of material that we post on Canvas that tells you these are the things that you really need to know. These are the kind of problems you need to know. And if you're having any trouble finding the reference material that you need, by the way, there's a lot of it in these textbooks. There's a lot of it on the internet. Most of if you have any question about any book or reference material you're using is appropriate and helpful. Just check with the instructors to help you out. And in some sense of the way, the homework is designed to be the material. In some sense of the word, we give you the homework, not expecting that you've already read some book and you now understand it, but that you'll contend with the material in the context of that homework, and then having mastered the homework, you'll then create similar material from the exams. Okay, logistics, that's all I have. Waiting for somebody like really has a desperate question, otherwise I'll carry on. Okay, cool. All right, so let's start with Einstein's special relativity. In order to do that, I need to remind you of what classical relativity is about. I'm going to move I have no idea if this is working or not, but we'll see. So I'm moving my laptop so you can follow the chalkboard if I move. I don't know if that'll work or not. I have no idea. But we'll talk. Standing here, we're going all the way to. All right. We can try to move the chalkboard again. All right. So first of all, let's talk about relativity. of course, when we see relativity, you think Albert Einstein, the most famous physicist of all time, by definition almost, and pretty much worth it. If you look what he did in his life, it's really hard to I think you have to say about Albert Einstein when it comes to his impact on physics. There was just the number of topics he covered, the things that he did when he was young, the things he continued to do throughout his life. It's just an amazing accomplishment. And anybody who's is a fan of the history of physics cannot but be impressed by it. But Einstein didn't just work in a vacuum. There are things going on, and the idea of relativity as a concept is actually an old idea. And so, depending on which flavor of physics 121 or the fundamental or the functional equivalent of Newtonian course in Newtonian mechanics you've taken, you have either more or less emphasis on relativity as a concept in kinematics. So what do we mean by relativity? And relativity, at least in the context, what Galileo wouldn't have recognized the lecture I'm giving here, but he was one who basically first articulated the concept. So we're going to, the convention is to basically say, okay, there's this notion of classical relativity, which is often named Galilean relativity. And what's the idea? So the idea is that motion is relative. And that comes out of just writing down coordinate systems and trying to figure out what's going on. So if I have a coordinate system, here's a coordinate system X and Y and Z, and I'll label the coordinate system O. This is consistent with the textbook that I recommend. Some other textbooks will label this coordinate system F or R, different labels for this coordinate system. And I can say, okay, let's talk about a particular point P that appears that corresponds to the location of a particle. For example, let's start with a classical notion. There's a particle, a fly, buzzing around the room if you want. This corresponds to the particular location of that particle as a function of time. So, and it's some particular point in time. So to describe that fly being at that location at a particular point in time, then I have a set of variables which I can say X and Y and Z and T. In other words, where that fly happens to be at a particular time is drawing that can be described as these coordinates as a function of time. And then once I've done that, I can ask all kinds of questions like, how do these quantities vary as a function of time? Calculate things like position, velocity, acceleration, and then I can start to do classical mechanics. And that's cool. And by the way, you remember from your classical mechanics, I'm just doing this kind of as a fill in the blank to show how, occasionally I'm going to do some simplification. In order to do the simplification, I have to basically tell you what I'm clearing away. So you remember that when I have a particle in three-dimensional space, I can represent that particle's position as a vector quantity. So the generic representation is R of t, where R is the position from the origin to the location of the particle. So that's R, which is the general function of time. Now, for the rest of the discussion on the classical thing, everything I'm talking about is a function of time. But it's just a function of time where it's like rolling a movie. It's like at any given point, I can take a snapshot, and at that particular frame, that's a time, and I can talk about position X, Y, T, or any of these other points. Now, suppose that the next thing I do is I come along and I say, okay, I've got another coordinate system that I'm going to put somewhere else. So here's my other coordinate system. I'm going to put it up here. And this coordinate system, I'm going to use the same. First of all, to avoid extra complication, I'm going to keep the coordinate systems lined up the same way. In other words, X, I'm not going to tip it at some screwy angle. That makes life more complicated. But for, I will nonetheless distinguish this coordinate system from the other one by leaving these coordinates as prime. This is X prime, Y prime, Z prime, and we'll call this whole thing O prime. Okay. So here's the second coordinate system. Now, the first thing we can do is we can say, given that the coordinate system is there, what can I say about the nature of the position of the particle? So this particle can be described by these numbers x, y, and t, but can also be described by x prime, y prime, and z prime, which are different numbers because this other coordinate system is over here, not over here. With me? Okay. And if I were to draw graphically, if I were to draw the vector that corresponds to the position vector of this particle with respect to this coordinate system, that's a position vector that goes from here to here. Okay. So I'm going to call that vector r prime. Again, because it's not this, it's a function of time. And then finally, I'm going to say, okay, there's another position vector in all of this, and that position vector is the position vector of the prime coordinate system with respect to the unprimed coordinate system. In other words, there's an offset, a physical offset component O prime, and I can draw that vector as well. That's a big line, something like this, and make it kind of fat. And I'm going to call this vector capital O. This is the vector. So let me make sure of this. All right, so I've made a big triangle here. I basically said two arbitrary coordinate systems displaced as a function of position at some particular time. And the displacement between the coordinate systems big R and the position of the particle I'm interested in is R, and the position of the particle I'm interested in seen by the other coordinate system is R prime. Now, once I've drawn this triangle system, it's continued for me to basically write down a rule that corresponds to how do I go from R to R prime. And the answer is I just use the vectors that basically go in this particular direction. So this one goes from here to here, and this one goes from here to here. And if you stare at it, that means that this vector here is basically this vector minus this vector here is basically this vector. So we got to basically go over here, and then we've got to displace in the same right way. So we can basically just draw here so I can basically turn it out. In other words, R prime is equal to the vector R minus R. Okay, so in other words, the way to think of it is I'm basically here. You want to see the path. Okay, so that's RT, and then I basically make a parallelogram like this. That's subtraction of R. I'm basically going in the negative direction of R. Okay. So this is quite general. If I want to transform from one coordinate system to another, I do subtraction. What do I subtract? I subtract the vector that gets me from the original to the transform. In other words, this is the old, this is the new. To get the new position from the old position, I subtract the difference between the coordinate systems. Okay. All right. So cool. Well, let's add another feature here. If I basically say, all right, for Galilean relativity, what we will say is that that the frame O prime moves with constant velocity, which I'll label V. Okay. So this, so now adding a complication, this whole coordinate system is now moving at some sense of word for starters, arbitrary velocity at some arbitrary position. So then I can basically write down an expression for R, right? So in other words, it must be true. If this is true, and the coordinate system R which is moving with constant velocity, it must be moving from its original position R naught, and then it is moving with velocity v times t. So in other words, as a function of time, this vector R is going to. So once I get past this, then I can just start taking derivatives. Take some derivatives. So I can now start asking questions like, okay, what are now that I've got the position, what can I say about the rush? So I'm going to take this, I'm going to take the time to this. So I take the time derivatives of both sides. So the time derivative of R prime is just p prime, by definition, right? Remember, this is the time derivative of the position. So I just say v prime, that's got to be equal to to take the time derivative of this, that's just v. Again, these are vectors, minus the time derivative of this. Well, that's just v. Okay. So now I have a transform rule for the velocity. In order to get the velocity in the time frame, I calculate, given the velocity in that time frame, I just subtract the velocity of the moving train. Again, this is very distant practice here again. Okay. And then I take one more derivative. Again, ddt on both sides. And I get a prime equals, well, this is constant. That's what I said, constant. So this is just a. Okay. This is the fundamental. What I've done is that we articulated Newton's law for the importance of the definition of fundamental inertial reference frame for doing Newtonian classical Newtonian mechanics. In other words, Newtonian mechanics is a mechanics that works in any inertial reference frame the same. And the reason it works is because if I take two derivatives of any kinematic quantity, I will then have an acceleration which is independent of the reference frame. Doesn't matter whether I'm standing here with this reference frame or I'm flying through the air with that reference frame. If I ask the question, what's the acceleration of this particle? I will get the same answer in both references. Okay. And by the way, so there's some sense where the fact that the answer does not change if I go from one reference frame to the other. This is known as in the language of physics, this is known as being invariant. In other words, the acceleration is invariant in Galilean relativity. Right? And technically, when I have a set of rules that basically define how you're going to go from position to go from one set of coordinates to another set of coordinates, this set of rules is called transform. So what I've basically done here, what I'm kind of showing again, remember I told you I'm doing a little bit of hand waving, a little bit of not quite so formal as all that. What I've basically demonstrated is that the acceleration is invariant under what we call classical or Galilean transform. Okay. Oh, and by the way, if I then just multiply both sides by m, the mass, presumably invariant mass, because classical relativity, I could say that, if I say, okay, that means that m times a prime is equal to n times a, so that means that the force in the prime reference frame is equal to the force in the unprime reference frame. So in other words, this is basically Newton's second law. Newton's second law that says that the forces are invariant. Okay, so this is the nature of relativity in classical mechanics, in Newtonian mechanics. That to go from one reference frame to another, you take some derivative, you basically do a subtraction, and then you take the derivatives, and you will find that the accelerations are the same, and therefore quantities that depend on the acceleration are invariant. And notice that all these definitions, even though these quantities in fact are functions of time, like to take derivative, the position itself of the particle, I'm going to say it's some sense of the word, the concept of where that particle is, as it is, this idea that it's just a simple dependent function of time. In other words, time itself is moving forward at an absolute scale. In other words, in all of this, it doesn't matter which frame you're in. The assumption is that we all have the same clock. Tick. I come and the person who's on this coordinate system has the same watch and synchronized their watches. And for all future, as long as those watches are working perfectly, that person can go off and come back. All kinds of crazy things can happen in classical mechanics, classical vision. Time isn't distorted in any fundamental way by being on a moving reference frame. It's something absolutely. All right, so that's classical. Now, so what we're going to do next is we're going to motivate what I will call the toolbox. One last thing I have to do. An additional simplification because it's useful. And these are some locations because it's useful. Everything I've shown here is quite general for arbitrary position vectors and coordinate systems and arbitrary locations and so forth, so some arbitrary velocities. It works. I just want to demonstrate because it's so easy. I could be quite general about it. What we're going to do in special relativity, however, what you'll see is that the transforms are mathematically more sophisticated. And because they're more sophisticated, it's helpful to have this level of simplification in constructs of the moving coordinate system. And the way that we're going to add this construct is that we're basically going to say, basically for O and O prime, at t equals 0, x equals 0, these are the x equals 0 equals x prime. In other words, the coordinate systems are going to line up and start at the same rate at the same time at time t equals 0. So now I'm not going to have an arbitrary value right now. I'm going to set this equal to basically a 0 like vector. And the second thing I'm going to do is I'm going to take this vector b, I'm going to translate it into a vector u times I hat, which basically means I'm going to constrain the motion of the moving coordinate system so that the velocity is simply a fixed speed in the x direction. And this may seem like an artificial constraint because, of course, by definition, if I put down a coordinate system, the body could be moving anywhere, or a coordinate system could be moving anywhere. But once I know when the way the coordinate system is moving, once I know a body or reference frame, which I know which way it's moving, I can pick a coordinate system that it's lined up with. So we're not really much of a loss of generality. And this simplifies the transformation. And in particular, without going into details, it's quite easy to show that if the motion is only in the x coordinate, then all subtractions are basically done in the x coordinate. There's no offset that has to be basically added to the problem. So I can write down a revised version of the transports and so on. And the same format. Okay, so I could basically say under these simplifications, in some sense, with the Galilean transform can be written like this. It basically says x prime is equal to x minus u times t, and then y prime is equal to y, z prime is equal to z, and t prime is equal to t. So all I've done is say I've got rid of the vectors, and I just did it component by component. With me, yes. And the only component that makes a difference is the one that is affected by the motion of the coordinate system in the x direction. But I'm adding to say that this is the last one. Starting them both the same place at the same time. And since the coordinate systems are only shifting in x direction, y, z, and t don't change, and the only thing that changes is x, and x just changes linearly as a function of time. It's the simplest possible transformation. You just take the old position, to get a new position, you take the old position, you subtract how far the coordinate system is going. The way I like subtraction gets people, the way I like to look, you're in a car, yeah? And you're going faster. If you're, how do I put it? If you're in a car and you're moving, and you ask the question, what is the speed of the things as measured in the car? Then it's the speed of the road minus the speed of the car. Notice, the things that are sitting on the road are zero velocity in their own frame. They're moving backwards in your frame. You're going over them forward, so they're moving relative to you backwards. Okay, so this is the Galilean transform. All right, so now next piece we want to do. We want to talk a little bit about the future. So again, kind of skipping a bit. So a couple of things that are worth pointing out. So in the context of all this, a few things. So the first is the notion of electromagnetic waves and the understanding of what electromagnetic waves are and how they work. And in particularly an understanding of a deeper understanding, mathematical understanding of mathematicals, well, really, not really that much deeper. Maxwell pretty much had it pinned out, but there was this increasing realization that you could that Maxwell's equations, in some sense of the word, stood on their own. So I'm not going to go back and do Maxwell's equations, and I know most of you have taken a course in the Physics 122 or some of the course where you have not yet had direct experience with the differential forms of Maxwell's equations. So the differential forms of Maxwell, so this, if I were to write down Maxwell's equations, the differential form, okay, the form that corresponds to the application of vector. Make it kind of like this, now, E, Q closed, not, so. Now we're gonna write them down. I'm not gonna write down the general equations. Equations in a vacuum. No charge, no current. So then del dot E is equal to 0. That's Gauss's law. Del dot B is equal to 0, which is the no main law or the no monopoles law. These two equations basically tell you that the divergence of the electric and magnetic field in the absence of charge is 0. It's bounded. Something you're not familiar with, freak out not, because I'm not going to give you problems. I'm just showing how to put the easiest way to get to the idea of electromagnetic radiation. The easiest way is through the differential forms. And then there's corresponding terms for the cross product. So del dot E is, yes, that's the one. That's 1 over, careful. Del dot E there. Negative B T, that's a partial derivative, and del cos B is equal to 1 over mu naught epsilon naught delta E delta T, delta T, partial E, partial T. Now again, freak out not if this is math that you haven't seen before. I'm guessing most of you are kind of tripping on it now in your math classes and stuff. I'm not going to make you work. I'm not going to make you in this class work vector identities and so forth and so on. But let me just explain what these two equations say in physics 122 language. They say that the electric field that is created in a tangential direction is proportional to the change in the rate of the magnetic field. Notice if I change the magnetic field, I get an electric field. And this equation says that the tangential component of the magnetic field is equal to, well, another constant times the rate of change of the electric field. So this is the, the magnetic field is changing, so it creates an electric field. The electric field is also changing, it creates a magnetic field. The two support each other in a mathematically consistent way, and the thing that you get is a changing electromagnetic field, which is a wave. Okay. Am I done? Am I out of time? Pretty much, yes. Okay. So we do. Oh, that's cool. So the question then becomes, what's waving? What's waving is the electromagnetic field. But this is happening in a vacuum. And the idea that things could wave in a vacuum, like I said, waves, classical physics, the ideas in the 1800s, every wave that you could point at, from sound to you name it, propagates as a disturbance that's propagating on a vacuum. That's what it means to be a wave. You have a displacement of a medium that's in equilibrium. And this question was then raised by Einstein. What is waving? What do you call that? Well, there's a name for it. They call it the ether, some luminous ether. I'll write it down in the website. And then the fun again, can we detect it? Can we see it? And indeed, a major, important, critical attempt to make that measurement was done right here, only a few tens of meters from where we're standing, the Michelson-Morley experiment, which utterly failed. The worst, the most famous